The goal of this video is to talk about calcium-induced calcium release, which is the process that initiates contraction of myocardial contractile cells of the heart. So let's take a look at this. This cell right here represents a myocardial contractile cell, which I often abbreviate as an MCC, very similar to skeletal muscle fibers, where we have the sarcolemma, cytoplasm. We have the sarcoplasmic reticulum here that is storing calcium. It has a high concentration of calcium compared to the calcium within the sarcoplasm. Riddled along the sarcolemma or plasma membrane are voltage-gated sodium channels. And here we have a voltage-gated calcium channel. Within the sarcoplasmic reticulum, we do have the ryanodine channel like we have in skeletal muscle. The big difference is in skeletal muscle, the ryanodine channel is a mechanically gated channel. If you recall, the conformational change in the DHP receptor pulls on that chain or tether to open up the gate of the ryanodine channel. But it's different here in MCCs. The ryanodine channel in MCCs, specifically within the sarcoplasmic reticulum of the myocardial contractile cells, is a ligand-gated channel. Additionally, we do not have a DHP protein within myocardial contractile cells. In place of that, we have this voltage-gated calcium channel. So let's take a look how this process works. First, we're going to have an influx of sodium into this cell. Influx of sodium is going to depolarize the cell. Once the periphery of the cell is depolarized and it has traveled down the T-tubule, we will get an opening of the voltage-gated calcium channel. So we're getting extracellular fluid calcium moving into the cell, moving into the MCC, and that proceeds to dock on its binding site, which is the ryanodine channel. So the ryanodine channel, as I suggested, is a ligand-gated channel. And the ligand it is sensitive to is calcium, specifically extracellular fluid calcium. When calcium binds to that ryanodine channel, it opens up the channel, allows calcium to move from the sarcoplasmic reticulum into the sarcoplasm, bind to troponin, move tropomyosin, and allow contraction of the myofilaments and of the muscle fiber, or the muscle cell. All of that, once calcium leaves the sarcoplasmic reticulum and binds to troponin, is the same as we talked about in skeletal muscle. So I'm not going to go over that aspect again. You can look at that and listen to that in the previous video on skeletal muscle contraction. So one thing I left out is what causes the initial opening of these voltage-sensitive sodium channels. That is the big question, and we'll talk about that in another video. But a quick trailer to that, I will just say MACs, myocardial autorhythmic cells. So now we've just had this the cardiac muscle fiber contract, which is allowing the heart to beat. But we need to restore everything like we do in all other excitable cells. In skeletal muscle, we had the sodium-potassium pump, restoring the gradients of sodium, moving sodium back out of the cell. And we also had the calcium pump, pumping calcium back into the sarcoplasmic reticulum. And that is no different in this cell, but we have something a little bit different. That is to say, we need to get calcium, the extracellular fluid calcium that came in, back out of the cell. Now, truth be known, calcium is calcium, whether it's from the extracellular fluid or the sarcoplasmic reticulum, but I've just color-coded them in two different colors to remind us where that calcium has come from. Calcium is pumped back into the extracellular fluid by a co-transporter which is also an antiporter, known as the sodium calcium exchanger, the NCX. And the NCX uses a kinetic energy of sodium moving down its gradients into the cell, specifically 3 sodium coming in to pump 1 calcium out of the cell. Now, certainly there's going to be a number of these antiporters, and it's going to be functioning over and over and over again. So we're going to be getting rid of more than just 1 calcium. But the sodium calcium exchanger exchanges 3 sodium coming into the cell down its electrochemical gradient, creating kinetic energy in the process that propels or pumps calcium back out to the extracellular fluid against its gradient. Now, the 3 sodium coming in is significant because those 3 sodium that come in, if nothing was done with those 3 sodium, that would depolarize the cell at a moment in time where we do not want the cell to depolarize. Keep in mind, this is in the state of relaxation of this MCC, but fortunately, these 3 sodium that come in will immediately get pumped back out via this, which is our favorite channel of all, our favorite pump, the sodium-potassium pump. It's going to pump those 3 sodium right back out of the cell. So that's how we get rid of the calcium back into the extracellular fluid or back out to the extracellular fluid. Don't forget, we still have the calcium pump or the calcium ATPase that moves calcium back into the sarcoplasmic reticulum. Okay, that is contraction, excitation of MCCs.